So welcome to our tutorial on data sketching for real-time analytics, theory and practice. I'm Daniel Ting, and with me is John Malkin. To let you know a little bit about ourselves and the perspectives that we're coming from, I come from a background in statistics and machine learning, and I was initially inspired to work on data sketching for my time at Facebook, where problems of scale appeared over and over again. And data sketching was one of these ways to deal with some of these problems. Since that time, I've moved to Tableau Research to spend more time on developing sketching algorithms and theory.
My background is originally in speech recognition and machine learning. I found sketching after I was tasked with improving the process by which Yahoo, now a part of Verizon Media, counted unique visitors when I met Lee Rhodes, who had recently started exploring sketches to improve the scalability of metrics calculations. Since then, I've moved to working directly with Lee as a contributor to Apache Data Sketches. Lee, the founder of what is now the Apache Data Sketches project, also contributed to this talk.
And our hope is that regardless of whether or not you're interested in applications and building systems or in algorithms and theory, you'll learn something useful, or at the least something very cool from this tutorial.
So for this portion of the tutorial, I'll be talking mostly about some theoretical and algorithmic aspects of data sketching. But before we get to the contents, I'd first like to thank a number of researchers and collaborators who I've had the pleasure of working with or learning from over the years. And in particular, some of these researchers have done some foundational work in data sketches, which researchers like myself are now able to build off of. So why might you consider data sketching? The main problem that data sketching tries to solve is this problem of big data. And as you know, there's a tremendous amount of data being collected and stored in the world right now, and it continues to grow. And although systems have now been engineered that are capable of ingesting, storing, and running massive queries on big data, these systems are also being subject to increased demands due to the number of analyses increasing, and more analysts using these systems, and the more pipelines that are built off of them. And this results in problems in providing scalability and speed at affordable costs. And engineering-based solutions to this problem always hit a fundamental roadblock. Namely, that in order to execute these queries over big data, you simply need to spend a lot of time reading big data. So data sketching is a way to attack this fundamental problem by making big data into small data. And this opens up some intriguing questions. For example, what possibilities might be opened up if speed and cost are no longer worries? Would you now be able to provide real-time analytics? Would you be able to build new user interfaces or perform automated analyses that previously would have hammered your system, but now can be run comfortably? And in general, what problems would you potentially tackle that you might not have tried before? To define data sketches, I'll give a very general definition. A data sketch can be considered any sort of lossy compression or summarization of data. And all that's required is that this summarization is able to provide answers to some set of questions of interest. The advantages of using data sketching can be quite significant, providing benefits in both space usage and in processing speed. For space, it can reduce the space usage by orders of magnitude, multiple orders of magnitude. And for speed, typically these sketches can be built in one pass and in a parallelizable fashion, and when it comes to query time, it's usually nearly instantaneous to read from them. At the same time, these sketches are not a panacea. There is no free lunch. In order to achieve these space savings, the information that the sketch stores necessarily reduces the amount of information in the full data. And because of this, the sketches typically can only answer a particular subset of questions or queries, and these queries must often be determined in advance. At the same time, the lossy compression necessitates approximation error in many of these sketches, though often this comes with a theoretical bound. To get a sense of the advantages and limitations of sketches, we can first look at some basic examples that everybody should be familiar with. One example is a simple random sample. Almost any question that could be posed on the original dataset could also be posed on the simple random sample, and the answer simply has some approximation as error associated with it. Another example is histograms. Histograms provide an excellent example of the types of trade-offs that could be made with sketches. It produces a very small summary of the data, which can answer a wide range of questions about a univariate distribution. For example, it can be used to compute the mean, the median, identify if there are outliers or heavy tails, or identify possible modes. At the same time, if you had a question which involved multiple dimensions, the histogram would essentially be useless for that type of question. Other examples include pre-computed aggregates or parametric statistical models. And in this case, the statistical model encodes information about the distribution of the data without providing any specific data points. And while the previous set of sketches are typically used in very common analytic tasks, sketches can also be used in more complex data processing. In particular, there's a set of sketches useful for numerical linear algebra tasks, including those using random projections, sketch singular value decomposition, or in more advanced sampling techniques for accelerating regression. Other advanced methods include Nystrom approximations for coming up with low-ranks approximations to kernel matrices, various methods for constructing core sets that accelerate statistical or machine learning model fitting, and sketches for complex tasks such as for graph problems. To get a sense of the ways that sketches are used, here are a few applications of data sketches. These applications span a variety of disciplines ranging from computer networking to biology. In some applications, like those in network security or in genomic applications, data sketches enable analyses at scales that simply would not be possible or would be cost prohibitive if exact methods were used. For example, to detect a distributed denial of service attack, an exact method may require storing millions or billions of counters for every IP or pairs of IPs. A data sketch, on the other hand, may solve it using a frequent item sketch and or a distinct counting sketch in much less space. Other tasks, such as those in, say, databases or web applications, can involve much smaller data sizes. But in this case, data sketches are used to accelerate frequent operations or reduce the communication cost. For example, in databases, you may issue a query for a particular key or particular item, and a sketch can be used, an approximate set membership sketch can be used to determine what files you actually need to read or what can be skipped. And if the key is very unique, then most of the data that you would have read before would be able to be skipped and the query would be vastly accelerated. So for the rest of this talk, I'll be describing several sketches one by one. Most of these will focus on these sketches used for analytic tasks, but I'll touch a little bit upon the more advanced methods. I'll also touch a little bit about the relationship between differential privacy and sketches, and as we go through each of these, I'll highlight key techniques and takeaways as we go through them. So whether or not you're a researcher or a practitioner, our hope is that you'd be able to get something out of this tutorial. For practitioners, this may mean being able to better navigate the world of data sketches. So you may be able to better understand the capabilities of various sketches, or to better understand the types of guarantees that these sketches provide. This may help you also in choosing a sketch to implement. For researchers, given my background in statistics, I'll present a more statistical approach to sketching. And this will sort of impact how you see how sketches are constructed, as well as how you get estimates out of these sketches. I'll also talk a little bit about relatively new developments in the world of data sketching, as well as perhaps some open problems. So this brings us to the first class of data sketches we'll consider, those for approximate distinct counting. And these sketches are now pretty ubiquitous in databases, with some databases even offering press releases when they add this sort of functionality to their offerings. So in this approximate distinct counting or cardinality estimation problem, you're given a data stream or multiset where the items in the stream can be duplicated multiple times. And your goal is to compute the cardinality, or the number of unique items in this stream. As for this sketch and for every other sketch, the paradigm is essentially that I'm going to take this data stream X, try to process it in a streaming fashion to produce a sketch S, and this sketch can be stored, and I can recover an estimate for the cardinality or whatever quantity of interest is later by computing some function n hat of this sketch. To make this problem more concrete, we'll look at one of the most important applications of these distinct counting sketches, namely applications in online advertising. So if you're an advertiser, typically one of the things that you want to know is if I run an ad campaign, how many users do I actually reach? How many eyeballs actually see my ad? And this is because metrics which are additive, like total number of impressions, don't distinguish between a user which saw 100 and same ad 100 times versus 100 distinct users who saw the ad once. And obviously, due to diminishing returns, it's simply not as valuable to have a user that saw an ad 100 times. A second problem that advertisers face is the problem of estimating audience size. If an advertiser is already publishing ads with CNN and The Guardian, then they may ask, should I spend my additional ad budget on the Washington Post, another news site, or maybe a basket of blogging sites would yield a more diverse set of users. Furthermore, you typically also want to know something about the demographic breakdown of the audience that you're reaching. So if you're an ad placement provider, you need to be able to provide the advertisers using your service these metrics which they care about, these metrics about reach and audience size. And so if we look at the reach problem, we can see how to translate this into a database query and how it's executed to see how costly it is to perform an exact computation. So this problem of how many distinct users saw an ad can be translated to a simple database query which says select count distinct user from some very large stream. And to compute this exactly, the naive way to do this would be to take each user, insert it into a hash table, and after all the users have been encountered, you simply count the number of keys in this table. If you had 1 million users who saw an ad, and each user took up 64 bits, then a reasonable estimate of the hash table size would be about 16 megabytes per ad. But these ad placement services aren't dealing with just one ad. They may be dealing with 100,000 ads per day. And so 16 megabytes quickly blows up to 1.6 terabytes per day. And if you also need to provide historical information, this quickly grows to 50 terabytes per month. And if you wanted to add demographic breakdowns, this cost would increase exponentially. So we can look at what happens to the cost when we replace these hash tables with a sketch. So if I were to take these 16 megabyte hash tables and replace them with the hyperlog sketch with 4-bit counters, then my 16 megabyte hash table would suddenly become, say, 2 kilobytes in size. And these sketches would still be able to provide answers with relative error of 1.5%, meaning that if the answer was 1 million before, the new answer, or the estimated cardinality, would be roughly 1 million plus or minus 15,000. And this represents an 8,000 times improvement in space, so that before, where we faced storing 50 terabytes for every month, we can now only store 6 gigabytes, which is quite reasonable to store on just a single machine. So how do these sketches work? Well, in this particular case, the main challenge in building a sketch which works is how to handle duplicates. And that brings us to our first technique in sketching, namely hash-based or coordinated sampling. So hash-based sampling assumes that there exists a universal hash function mapping data items into IID uniform random variables. And as long as I have enough bits in my hash function, then I can be pretty confident that after hashing, I still have n distinct values or very close to it. But the purpose of this hashing is actually to take this data, which came from some unknown domain, and map it into a distribution that I know and which only depends on this desired cardinality n, thus preserving the information that I care about. Now, simply hashing doesn't solve this problem of needing to store n distinct values. However, since the distribution is now known, I can compute some sort of summary statistic and then use that to try to infer what the original parameter n is. And so the summary statistic, which is stored by one of the commonly used sketches, min count, or also known as the k minimum value sketch, is to simply keep the smallest k distinct values. And this sort of illustrates the general paradigm that you use when you think about data sketching as a statistical problem. First, I'm going to take data and I'm going to convert it into this random process with some known distribution. And I'm going to construct it in a way where the parameters of this distribution are exactly the answers to my questions of interest. I'm going to build this random process in a way so that it can be updated and stored efficiently. And once I have this sketch, now I simply need to apply the statistical tools at my disposal to perform a parameter estimation problem to actually extract these answers to the queries of interest. So to better understand the min-count sketch and how you can obtain a cardinality estimate from it, we can look at an analogous physical process. So imagine there was a beach full of trash, and you wanted to count the total amount of trash on the beach. An easy way to try to estimate this would be to simply take a bag, start at the beginning of the beach, wait until you've collected k items, or wait until the bag is full, and thus estimate the rate of trash, the rate at which trash appears on the beach. And you just take this rate and multiply it times the length of the beach to find an estimate of the total amount of trash. And min-count really follows this process almost perfectly. You take data items, you hash them uniformly into the unit interval, or equivalently uniformly along the beach, and this allows you to take the smallest k items, which are exactly the same as taking the first k items you see on the beach, and this allows you to estimate a rate at which items appear on the unit interval, or the rate at which items appear on the beach. And thus you can get a cardinality estimate. So more formally, the min-count sketch stores these k smallest values, z1, z2, up to zk, and it returns a very slightly different estimate. So it returns this estimate k minus 1 divided by zk, the location of the kth item. And what you can figure out with this estimator is that since I know the exact distribution of the zk's, I can actually find the exact distribution of this estimate. I can show that the estimate is unbiased. I can show that the standard error for this estimate is approximately n over square root of k minus 1, so that if I set k to be equal to 102, I know that I'll get approximately 10% error overall. Furthermore, I can actually show that this is the best possible unbiased estimator, namely that it's the minimum variance unbiased estimator using statistical techniques. And compared to other distinct counting sketches, this min-count sketch has a number of advantages and disadvantages. All of these stem from the sketch essentially being a random sample. The advantages of the sketch are that it's very flexible. It supports all set operations, including unions, intersections, set difference. You can even apply filtering to the sketch if you have some information about the hashed IDs. The disadvantages, however, are that this flexibility comes at a cost. This sketch can be much larger than other distinct counting sketches. They can be, for example, up to 15 times larger when you're dealing with large cardinalities, and you can have slightly worst case updates. And this idea is also of sampling is also the basis for the theta sketch and tuple sketches, which are also in the Apache Data Sketches library. The advantages and disadvantages of min-count speak to an inherent trade-off that's present in data sketches, namely that of flexibility versus efficiency. Since sketches use less space, it necessarily means that they've reduced the amount of information that's contained in them. And because of this, you can't necessarily answer all questions that you could have with original data, but you can only answer a subset of questions. And sketches must pick and choose what queries that it can or cannot answer. And this isn't necessarily a bad thing. For instance, most queries are probably not very interesting or rather useless. You might ask the data, perhaps, how many people queried for Apache data sketches, and also the phrase recipes for banana cream pie. While there is some answer that's present in, say, Google search logs, this question is not one which is of any interest to almost anyone. And so if you imagine there are so many of these sort of pointless questions, we can discard the answers to all of these and restrict ourselves to a set of questions or queries which are potentially interesting. And out of these potentially interesting questions, the sketch may even be able to further reduce the amount of information by only answering the ones where you actually have an interesting answer. So going back to this problem of distinct counting, we can look at the min-count sketch and see how we can trade off flexibility for efficiency. And we can do this through this technique of quantization. When constructing the min-count sketch, we essentially thought of the construction as being a two-stage process. First, you take data and then convert it to a random process, where the parameters of the random process encode the cardinality. Once you have this sketch representing this random process, you perform another stage which estimates the cardinality out of the sketch. What we'll look at now is another stage where we take this random process and then we look for a way to encode it efficiently so that it can be stored in smaller space and allow for fast access. So hyperlog is perhaps the most popular distinct counting sketch out there. And hyperlog improves upon the efficiency of min-count while trading away some of the flexibility. And it does so by making two modifications. First, rather than storing the k smallest hash values, it instead hashes each item into one of k bins and then just stores the smallest value in that bin. And what this does is that it improves the worst case update time, whereas before, if you used a heap to store the k smallest hash values, this may have required log k time in the worst case. Just simply hashing to one of k bins and taking them in is an O of 1 operation. More importantly, the values that are in these bins are quantized. And by doing so, you don't need to store, say, a full floating point number, but you can store a very, very small integer representing that. And by doing so, you can gain substantial space efficiency. To better understand the hyperlog sketch, we'll examine the effects of each of these modifications separately. First, we'll only look at the effects of the binning trick. And in this case, this continuous version of hyperlog, the sketch is represented as a vector in Rk. And the main difference is that when I hash an item, I'm going to assign it to a bin in addition to hashing it to some random uniform value. And the value in the sketch will just be the minimum zi value assigned to a particular bin. And when I want to estimate a cardinality from this sketch, I can use the exact same principles that I used to derive the min-count estimator for this continuous hyperlog estimator. Rather than look at the distance traveled until I see the kth smallest item, I can look at the distance traveled until I see the first item and average over the k replicates that I have. This gives me a rate at which I will encounter items in each of the bins, which I then just multiply times k to get the overall cardinality. And the nice thing about this estimator is that, like the min-count sketch, I can show that this continuous hyperlog estimator is essentially optimal. More precisely, if my cardinality was some number which was Poisson distributed with parameter n, then this continuous hyperlog estimator will essentially correspond to the maximum likelihood estimator for this parameter n. And as you might be familiar with, the maximum likelihood estimator is asymptotically efficient and so effectively optimal. Now if I add some quantization, this continuous hyperlog sketch becomes the actual hyperlog sketch. And for this quantization procedure, the only thing that changes is that where previously I might have stored uniform 0, 1 random variables, I instead take these uniform random variables and transform them by putting them on a log scale and then rounding by taking the ceiling. And what you'll note is that by performing this quantization procedure in the middle, because taking the minimum of quantized values is the same as quantizing after taking the min of a bunch of values, I can reconstruct this hyperlog sketch by first running this continuous version of the hyperlog sketch and then performing the quantization procedure afterwards. So in this sense, it's generating the exact same random process as continuous hyperlog, but this doing a further efficient encoding of the information in there. And this, of course, also changes the estimator that I get out, but you can still use the continuous hyperlog estimator as sort of a base for it. And basically, all I need to do is undo this quantization procedure in some way. And this can be done by essentially taking the sketch values and then rescaling them back to being between 0 and 1. And that gives me an approximate rate, giving me a decent estimator of the cardinality. However, this estimate is biased. And so to correct for that, I multiply this rate by this term alpha to correct for this quantization. And so for people who are familiar with the hyperlog sketch and have seen the formula for it, it initially seems very mysterious, but this sort of gives you a nice clean explanation about why this particular estimator has the form that it has. By comparing hyperlog and min_count, we can see what kinds of efficiency gains that hyperlog achieves by using this quantization. So for min_count and hyperlog, for both of them, we have good estimates of the error, at least for large cardinalities. For min_count, the error is approximately n divided by square root of k, whereas for hyperlog it's 1.04 times n divided by square root of k. And this is rather amazing because if I were to look at the continuous version of hyperlog, I would get the exact same error as for min_count. And so hyperlog after this discretization performs very nearly optimally. It only pays this factor of 1.04, despite throwing away information through this quantization procedure. However, it's able to dramatically reduce the size, whereas min_count used, say, 32 or 64-bit hashes and required k times 64 bits. Hyperlog is able to use counters which only use 4 to 6 bits. This gives savings of up to 15 times. However, min_count is able to support more operations, more set operations, including intersections, set difference, and filtering. And so this is the trade-off. You lose the ability to answer a few questions with min_count, but you get a pretty substantial gain in efficiency. So after seeing these two sketches, a natural question to ask is whether or not one of these two sketches could be considered quote-unquote the best. And what you'll find is that when you look at the sketching literature, the answer isn't so obvious. To illustrate this, here is a partial list of distinct counting sketches. You'll notice that there are quite a few, but the question is, which one of these should you pick? And I'll give you a little bit of time to look through these sketches and pick one that you think would be promising. So you might pick this optimal distinct counting sketch as your sketch of choice. But it turns out this quote-unquote optimal algorithm is highly inefficient even though it has optimal space complexity. And this speaks to a disconnect between theoretical results and practice. Whereas theoretical results often quote a rate, in practice the constant factors associated with the rates are often quite important. And it's actually the case that no one sketch dominates the others in all cases. For example, if you have a rough estimate of the cardinality, the linear probabilistic counting sketch would actually do much better than hyperlog or the sampling-based sketches. Or if you're in a purely streaming scenario, then the self-learning bitmap can be more efficient than hyperlog as well. Or if you only care about the amount of storage space that a sketch uses, then a compressed version of probabilistic counting would be better than a compressed version of hyperlog. However, hyperlog and these sampling-based sketches are simply particularly well-rounded sketches, being able to cover basically all scenarios pretty well. But even if you were to settle on just implementing hyperlog, in order to get a state-of-the-art implementation, you would need to make a number of improvements over the original algorithm by Flageolet et al. In 2007. For example, you might need to implement the sparse representation for low cardinalities from hyperlog in Hoyle et al. 2013. And rather than the 5-bit bins in the original algorithm, you might choose to use 4-bit bins using an offset idea from the implementations in Presto, Druid, and data sketches. You might also replace the estimator for cardinalities using an improved raw estimator from Otmar Erdl in 2017. And if you want tight error estimates, you might use the error estimator from one of my own papers in 2019. You might also compress the sketches using ideas from Shoreman and Mauve and Lang 2017. And in the case where you have the data coming as a single stream, the streaming historical inverse probability estimator would give more accurate results. And you can also get a tight error estimate from this from my work in 2014, and Edith's works in 2014 as well. And these are reasons why, even though an algorithm may be seemingly easy to implement, you may want to consider a well-tested library, which has both great engineers working on it, as well as researchers who are actively involved in its development. There are also cases where improvements to HLL have been proposed, but they may not be sensible for you to use in your use case. For example, HLL Telcop Plus does gain some efficiency in smaller space, but it does so by sacrificing the ability to do unions. Losing the ability to do unions is particularly problematic because it destroys a key property of practical sketches, namely that of mergeability. To define mergeability, consider a sketch construction algorithm S that yields estimates where the estimates have error of scale sigma. S is mergeable if there exists a function which will take two sketches, S of D1 and S of D2, both which provide estimates which have errors of scale sigma, and this function generates a new sketch S prime, whose estimate also has error of size scale sigma as well. Mergeability is a really important property because it enables distributed processing. For example, if my data was incoming to multiple servers, then I'd be able to sketch the streams at each server and then merge them together, thus eliminating a bottleneck in my processing. Likewise, if I have a huge data set, I may map them out to multiple compute nodes to compute the sketches and then merge them together in a final sketch. This also helps in reliability. For example, if for some reason several items in a stream were dropped in the middle, you'd be able to go back, process these items, and then add them back into your sketch. This also enables further aggregation. For example, if I were to look at a multi-day time window, say for a week, I'd be able to process sketches day by day, and after the fact, be able to aggregate them over the entire week.
And this brings us to the real problem that we typically face when we're using distinct counting sketches. The typical problem isn't that we need to compute a single distinct count, but rather that we need to store information that allows us to quickly query for the distinct count for many, many different possible sets. And it's this blow up in the number of distinct counting problems that I need to deal with that really makes the problem challenging.
So going back to this advertising problem of reach estimation, this changes the question from how many distinct users saw a particular ad to how many distinct users saw an ad broken down by the day they saw it, the user's age, gender, country, and device type. And when you have so many breakdowns, the number of counters needed per ad grows exponentially. So if I have 100,000 ads, this may require 15 billion counters. And with 2 kilobyte sketches, now I'm back in the case where I need 30 terabytes. And although sketches that only support unions require you to break down and assign a counter to the finest granularity of a breakdown that you might query for, more flexible sketches, in particular sketches that support intersections, are able to answer the same set of queries using far fewer counters. So in this case, rather than having to multiply the dimensions for every breakdown together by using intersections, I can simply add them up. So in this case, I only need 142 counters per add, yielding 14.2 million counters versus 15 billion. And so even if my sketch might be 1,000 times larger, I may end up with a comparable size as using, say, an HLL sketch. To get a picture of what space daisies you might have by using either the hyperlog or min-count sketch, we can look at this sort of pictorial diagram. On the left, we have the case where you compute cardinalities exactly. We have many, many counters, and for each counter, I need to store a hash table, which requires a significant amount of space. If I were to use a hyperlog sketch, the number of counters stay the same, but I can use far less space per counter. On the other hand, if I used a more flexible sketch, such as the theta sketch or the min-count sketch, I can dramatically reduce the number of counters and only pay, say, a modest price in the space usage per counter. And then the question is simply, which one becomes more beneficial in your particular case? And you might say that, well, if I support unions, in some sense, I can also support intersections through the inclusion-exclusion rule. And this is true. You can compute an estimate for the intersection using this rule. The problem is that these estimates are often terrible. The error tends to be proportional to the largest estimate, namely the estimate for the union. And so if you have two sets with a relatively small intersection, so if they have a Jacquard similarity of 0.1, and if, say, each sketch had estimates that have an error of 2%, then the estimated intersection you would expect to have error of approximately 20% of the intersection value. And this becomes even worse when you're taking multiple intersections. And this brings us back to the usefulness of sampling-based sketches. Like I've mentioned before, these sampling-based sketches tend to be significantly larger than hyperlog if I just want to estimate a single distinct count. But they're often much better at estimating intersections. Furthermore, when you compose these sketches, you can continue to take more and more intersections together, and the output is simply another sketch. So they have this added advantage that they're sort of closed under these set operations, and you can store the result of them by itself. And examples of these sketches include the min-count sketch, also known as the bottom K or K-minimum value sketch, as well as the theta and tuple sketches, which are implemented in Apache data sketches. However, using sketches that support intersections is not the only solution to this problem of computing many distinct aggregates for many, many sets. For example, using a sparse representation for low cardinalities may be sufficient for your problem. In this case, if you have many counters which have low cardinality, you're able to allocate less than, say, 2 kilobytes of space per counter. For these low cardinality sets, the counters only require space proportional to their cardinality. Another idea is this idea of counter sharing. In this case, rather than have each counter occupy its own space in memory, you have the counters share space in some fashion. And in this case, you're still able to answer cardinality questions for sets which have high cardinality accurately. However, sets which have low cardinality may not get a very accurate answer. And thus you sort of prioritize the estimation of sketches or sets which have high cardinality relative to others. So the second sketch that we'll look at is sketches involving sampling. And as alluded to before, the advantages of sampling are that when you use sampling, these samples are extremely flexible. Any question, or rather almost any question that could be answered using the original data could also be answered using the sample. Furthermore, samples are extremely easy to work with. Oftentimes, it requires no changes to downstream methods, except to add a sort of weight associated with each item. The disadvantages, of course, are that in order to get this flexibility, these sketches require more space than specialized sketches. And so we'll just cover this sampling very briefly, since other tutorials have also covered sampling. The canonical problem that sampling deals with is a problem called the subset sum problem. For example, it might answer, what are the total sales that have had a promotional discount for items with a promotional discount? Or what are the total sales by product category? In each case, I'm dividing up a sum which might have been total sales into different subcategories, namely items with promotional discount or by product category. And more formally, this just means I want to compute some sum where the sum is over indices from a particular set. And despite this simple form of this subset sum problem, it can actually answer many, many questions. For example, you can recast distinct counting as a sum. You can recast intersections as subset sums. And in some cases, you can convert parametric statistical or machine learning models into something which is asymptotically a sum. And the problem is really just, how do you do better than simple uniform sampling? To do this, we first provide an unbiased estimator for the subset sum that works for any sampling procedure. This estimator is the Horvitz-Thompson estimator. We can then look at how to construct a sketch or sampling procedure that minimizes the variance of this estimator. The Horvitz-Thompson estimator is a way to estimate sums for samples drawn without replacement. In this case, the items themselves are not random. Only whether or not an item is included is random. If we denote the inclusion of this ith item by zi, and the probability of inclusion by pi, then the Horvitz-Thompson estimator is the sum over items in the sample, reweighted by the inverse of the inclusion probability. And it's easy to see that this is an unbiased estimate, since the expected weight for each item is 1. So the problem now is to figure out what inclusion probabilities will minimize the variance of the Horvitz-Thompson estimator. And the technique we'll turn to now is probability proportional to size, or PPS sampling. So a probability proportional to size sample chooses item inclusion probabilities that are proportional to the magnitude of the items themselves. And these probabilities can then be rescaled so the sample has an expected size equal to a desired sample size k0. And what's key to note here is that larger items, which contribute more to the sum, are also more likely to be included. More specifically, any non-zero contribution to the Horvitz-Thompson estimator will have a constant value. And what this means is that there's no variability coming from the values of the sum, only from the number of values. More formally, if we look at the breakdown of a variance into the conditional variance and conditional expectation, then we see that it can eliminate one term in this breakdown. However, there are some challenges in applying these techniques in streaming settings. In probability proportional to size sampling, the inclusion probabilities need to be set in advance. And these inclusion probabilities depend on data X, which is unknown in advance in streaming settings. Furthermore, if you want to keep the sketch size or sample size fixed, then the inclusion probabilities need to continually decrease as you see more and more items. And in this case where you do have bounded sample sizes, items also can't be drawn independently. One item's inclusion necessarily kicks out another item. And in this case, the true inclusion probabilities are actually intractable to compute. So what sketches for sampling do is that they provide ways to draw PPS-like samples without replacement in bounded space. And they get around this problem of intractability by replacing the true inclusion probabilities with some sort of easier to compute pseudo-inclusion probabilities. And algorithms that do this include priority sampling and VAROP sampling. They also provide ways to extend these basic techniques. For example, if you had multi-dimensional items, you might use multi-objective sampling, which allows you to do well regardless of whether or not you're computing a sum over the first dimension or second dimension or any other dimension. So one last thing I'd like to do is to contrast Horvitz-Thompson estimation and PPS sampling with another commonly used technique, importance sampling. and to describe a little bit about when each is appropriate to use. So importance sampling is a way to estimate sums using samples that are drawn with replacement. And in many ways, it looks exactly like Horvath-Thompson estimation with PPS sampling. In both cases, you draw the ith point with probability proportional to the magnitude of that item. Except in importance sampling, you do so with replacement, and you choose inclusion probabilities so that they're rescaled to sum to 1, rather than to maintain some sort of expected sample size. And the disadvantage of importance sampling is that you can potentially have many duplicated items in your sample. So in this example, we have an item E whose weight is equal to half of the total weight in the data. And importance sampling in this case will waste half of the sample just repeatedly sampling the same value. And so if I have a subset sum query which doesn't include this item, my effective sample size is now half of what it could have been. Furthermore, if I have a query that includes E, now the contribution of E is random rather than fixed and exact. So both of these techniques still have their use cases. For Horvath-Thompson and probability proportional size sampling, these techniques are good when you have a fixed data set or some sort of discrete distribution. On the other hand, importance sampling is still useful when you're doing Monte Carlo estimation with a continuous distribution, and also in cases where, in theory, you need to prove something, and the dependence in the importance sampling technique makes the proof easier. Though in this case, if your distribution is discrete or you have a fixed data set, in practice you would still just substitute in and use Horvath-Thompson estimation with probability proportional to size sampling. So now we'll just take a quick break before we move on to the next topic of quantile sketches.